Okay, let's resume. So we've just seen that we can consider the chain complex of the universal cover as a right Z pi 1 module chain complex. And now let's take the first more algebraic approach of local coefficients, and let's consider modules over Z pi 1 and the effect of tensoring with these. So if we have a left Z pi 1 module, which I'll just call A, then we can form the tensor product of that with our the chains of the universal cover considered as a right module tensored over Z pi 1 with A as a left module. And we define this to be chain complex with module coefficients, I guess. This is a chain complex with boundary map just the boundary map from the C star of n tilde just tensored with 1, because this is just considered as a it's not a chain complex, it's just, or a zero-dimensional chain complex rather. And we call the homology of this chain complex, this is called homology of M with local coefficients in A. And in the case that we're obtaining A as the module associated to a representation, so in the case that A is A sub rho corresponding to the representation of pi 1 rho then we call this the homology of M twisted by rho. This is often called and we can do a similar thing with cochains. So similarly cochains. So instead of taking the tensor product, we have we take homomorphisms over Z pi 1 between the universal cover chain complex and A. And a technicality here, we need both of these to be left or both of these to be right modules, so we switch whichever one we like using this definition, and then we can consider this as homs from, say, a right module to a right module. And again, we can also have cohomology with twisted by rho in the analogous way. So let's do a couple of examples of the kind of things we can get. So let rho be trivial. Well, what effect does this have? So when we take the tensor product, we're identifying the action of z pi 1 on the module on the right with the action on the left. The fact that we've taken rho to be trivial tells us that z pi 1 acts trivially on A, and this means that we can transfer this action so that it should have trivial action on the left as well. So what this tells us is that if we quotient out by the action of the fundamental group, we just get the chains of the base space and tensored with just A with no action of rho, and this is now just a tensor over Z. So in particular, if we then look at this homology twisted by rho, this is just usual homology with coefficients in A. Well, coefficients in the abelian group A, forgetting the module structure, where this is defined as this, the homology of that chain. Similarly for cohomology, the next example of interest is what happens if we take A to be the group ring. Well, with the standard action, what we then get is that this is the tensor product of C star m tilde tensor over z pi 1 with z pi 1, and when we tensor over z pi 1 with itself, this is the same as just not having that there at all. So this gives us, if we take the homology of this chain complex, this gives us normal untwisted homology but of the universal cover. So and then also you can see that it's possible to show that any other cover of M, the homology of that can be obtained as homology with local coefficients for an appropriately chosen module. So now a little exercise. Or sort of a cross between an exercise and an example. So you'll have noticed from before that the orientation character, or the first Stiefel-Whitney class, is a representation. So we can form the homology of M twisted by the orientation character. I'm going to let Z sub W denote the Z pi 1 module associated to the first Stiefel-Whitney class. Now remember, that was a map from pi 1, a homomorphism from pi 1 to plus or minus 1, which is automorphisms of the integers. Now, the exercise left as an exercise because it's difficult, or at least for me, is to compute the homology with twisted by the Stiefel-Whitney class of K, where K is the Klein bottle.